Welcome friends to this fourth lecture of week 12 of soil science and technology, and in this lecture we will be discussing about how to model and different categorical variables in digital soil mapping, and we will try to complete this and then we will discuss about the pedotransfer functions. So, we will start from this slide where we left in the last lecture. Obviously, we started this categorical modeling, and let us see in details about how to measure different types of important quality measures in case of categorical modeling. So, there are 4 different types of quality measures in case of categorical modeling. One is called the overall accuracy, then users accuracy, then producers accuracy, and kappa coefficient of agreement. So, let us see them one by one. So, overall accuracy, let us consider this example. Let us consider there are 4 different soil classes D, V, CH and Ku. They are the names of 4 different soil classes. So, these matrix is called confusion matrix, which basically shows how many of the samples of using our categorical model have been correctly classified. Classification is basically assigning a particular observation correctly to their respective classes. So, classification is term used when we use categorical variables, and regression is term when we use continuous variables. So, here you can see we have classified several soil classes into their respective classes, and these are 4 different classes D, V, CH and Ku, their names. And if we summed each of the columns, so this is a column, this is another column, this is another column, this is another column. So, if we sum each of the column, we would obtain a total number of observation for each soil class. So, in case of D, we will get 8, V 20, CH 32, Ku 23. So, these are the total number of observation for each soil class. So, similarly, if we summed up each of the rows just like this row, this row, this row, this row, we retrieve the total number of prediction for each of the classes. So, if we sum again all the columns, we will get the total number of observation for each soil class, and if we sum all the rows, we will retrieve the total number of prediction for each soil class. So, what is the next step? The next step says the overall accuracy. Now, another important thing I should mention that these diagonal values basically represents in the matrix basically indicate the fidelity between the observed class and the subsequent prediction. That means the 5 samples have been correctly classified as D, 15 samples have correctly classified as V, 31 samples are correctly classified as CH, and 11 samples are correctly classified as the Ku samples, and all other off diagonal samples are misclassification, that means incorrect classification. So, numbers on the off diagonals indicate a misclassification error, and overall accuracy is therefore computed by dividing the total correct, that is a sum of the diagonal, by the total number of observation, sum of the column sums. So, if we divide the total correct classification, that is sum of the diagonal, by the total number of observations, sum of the column sums, then we will get the overall accuracy. In our case, this is 75. So, this is one of the measures of classification accuracy. The next measure is called producer's accuracy, but before the producer's accuracy, let us see what are the other important aspects, like accuracy of individual classes can be computed in a similar manner as that of overall accuracy. However, there is a choice of dividing the number of correct prediction for each class by either the total, that is observational predictions in the corresponding columns or rows respectively. Traditionally, the total number of correct prediction of a class is divided by the total number of observation of the class, that is column sum, we have already got the column sums for individual classes. So, this accuracy measures indicate the probability of an observation being correctly classified, and it is really a measure of omission error or the producer's accuracy. This is because producers of the model is interested in how well a certain class can be predicted. So, this is called producer's accuracy. Again, the producer's accuracy is computed when the total number of correct prediction of a class is divided by the total number of observation of that class. I have already told you the correct predictions by indicating these diagonal values or diagonal in this confusion matrix. However, when we take the ratio of these correct predictions of a class with the total number of observation of the class, we will get a producer's accuracy. Another important term is user's accuracy. Now, alternatively, if the total number of correct prediction of a class is divided by the total number of prediction that were predicted in that category, then it is result, then this result is a measure of commission error, commission error or user's accuracy. And this measures is indicative at the probability that the prediction of the map actually represents that particular category on the ground or in the field. So we have covered the overall accuracy, then user's accuracy, then producer's accuracy. The fourth important point is kappa coefficient. Now, the kappa coefficient is another statistical measure of the fidelity between observations and predictions of a classification. And the calculation is based on the difference between how much agreement is actually present, that is observed agreement, compared to how much agreement would be expected to be present by chance alone, that is expected agreement. So, we calculate this kappa coefficient by the difference between the observed agreement and the expected agreement. Again, the observed agreement is the how much agreement is actually present, and expected agreement is how much agreement would be expected to the present by chance alone. So, the observed agreement is simply the overall accuracy percentage. In our case, we have calculated already that overall accuracy is 25%. So, we may also want to know how different the observed agreement from the expected agreement. Now, the kappa coefficient is a measure of this difference, standardized to a lie between -1 to +1 scale. So, again this kappa coefficient takes a value from -1 to +1, where 1 is the perfect agreement, 0 is exactly what you be expected by chance, and negative values indicated agreements less than a chance. Again, +1 is a perfect agreement, 0 is exactly what would be expected by chance, and negative values indicate the agreement less than chance. That is potential systematic disagreement between observation and predictions. When there is -1, that again suggests that is a potential systematic disagreement between observation and prediction. The kappa coefficient is defined by this small k, and this P0 minus P by 1 minus P, where P0 is the overall or observed accuracy and P is the expected accuracy, where P can be calculated by using this formula, where TO is basically the total number of observation and N is the number of classes. In our case, the number of classes is 4, total observations we already know, and then column sum for individual and then row sum for individual, and then we will get the kappa coefficient. Now, once we calculate the kappa coefficient, what is the next step? What are the different cutoff values of kappa coefficient? The kappa coefficient has, as a rule of thumb, the scientists have devised certain cutoff values for kappa coefficient. First of all, when there is less than a chance of agreement, and you can see when the value is 0.01 to 0.20, there is a slight agreement, 0.21 to 0.40 fair agreement, 0.41 to 0.60 moderate agreement, 0.61 to 0.80 substantial agreement, 0.80 to 0.99 almost perfect agreement. However, where it is less than 0.01, there is less than chance agreement. So, These are some cutoff values for kappa coefficient. So, once you calculate the kappa coefficient, you can predict whether there is how much the strength of the agreement you can calculate based on these cutoff values. Now, for the classification of soil, or the categorical classification of the soil, it is very important to know a particular term called terrain. Now, terrain relates to a soil and landscape concept that has an associated model. So, the embodiment of terrain is a continual soil landscape unit or class which combines soil knowledge, landscape information and their interaction together. So, this is very important term. Now, before going to the applications of categorical model, let us consider a couple of categorical models. So, the first important categorical model we will talk about is logistic regression. So, remember that there are many important research topics for which the dependent variable is limited. For example, voting, morbidity or mortality and participation data is not continuous or distributed normally. So, binary logistic regression is a type of regression analysis where the dependent variable is a dummy variable coded 0 or 1. For example, if you want to know whether there is a two outcome, either they have voted or not voted for a particular candidate, you have to, there are binary outcome either voted or not voted. So, you have to code them either 0 and 1. 0 means either did not vote and 1 means vote. So, these are binary coding, we call it binary coding. So, you can see the output is very much limited, we have binary outputs. So, if we use the linear probability model, ordinary least squares regression, we will get this gamma plus phi x plus e, where y in our case is only 0 to 1. And the error term is heteroscedastic. So, you can see here y is only 2. I mean the values the y can take is only 2. So, E in this case you will see if we use a linear prediction model, the error will not normally distributed because y takes only 2 values. But this normal distribution of error is very much essential assumption for linear regression. However, in this case we will not get it because we are getting two binary output either 0 or 1. So, the predicted probabilities can be greater than 1 or less than 0. But we know that probabilities always lie between 0 to 1, it cannot be less than 0 or greater than 1. However, if we have only these binary outputs or limited outputs, we will get these some absurd probabilities. For example, let us see some example. I have seen this example recently, so I am using this for your better understanding. There is a questionnaire where they have asked people whether they will evacuate to some place some safer place if there is a hurricane. So, there are 4 options: yes, no, don't know or refused. So, the data looks like this. So, here you can see the evacuation, either they will they will not evacuate, they are they are denoted by 0, and evacuate they are denoted by 1. So, these are binary codings you can see. So, this is our target class, either evacuate or not evacuate. What are the predicted variable? Number of pets. So, you can see here the number of pets, mobile home if they have mobile home, then they have tenure in this of this home and their education. So, based on these particular for 4 different variables, we have to classify either they will evacuate or they will not evacuate. So, if we use the ordinary least squares regression or linear regression, ultimately we will get these coefficient values. And if we use these coefficient values, ultimately you will see for some and we create a regression relationship, we will get for certain number of numbers of subjects and certain number of n, we will get minimum maximum values, which is you can see minimum values here less than 0, which is not possible. So, this is the predicted values outside the 0 to 1 range. So, this is the problem in case of ordinary least squares. when we are having limited numbers of outcomes. So, what is the solution? The solution is to use logistic regression model. So, the logit model solves this problem, where we use this form of logarithm, natural logarithm of p by 1 minus p, and we use this alpha plus beta x plus e. So, it is a linear regression formula, and only in case of y we are using this logarithm of p by 1 minus p, where p is the probability that event y occurs. So, y equal to 1, this probability is p, and p by 1 minus p is the odds ratio, or simply we call odd, and natural logarithm of p by 1 minus p is the log odds ratio, logs of odd ratio, or logit. So, it is basically logit, and this logit is basically modeled by linear regression form. So, instead of targeting a particular target variable, we are basically converting them into logit, and we are predicting this logit using the simple linear regression or multiple linear regression. So, this is called the logistic regression model. Now, the logistic regression constraint the estimated probability to lie between 0 to 1. This is the solution, because we see that in case of ordinary least squares, the probability will go beyond 0 to 1. So, to cap them within 0 to 1, we need to apply this logistic regression. The estimated probability is obviously p equal to, if you simplify, it will be p equal to this. So, if you let alpha plus beta x equal to 0, then p equal to 0.50. So, as alpha plus beta x get really big, p approaches to 1, as alpha plus beta x get really small, p approaches to 0. So, you can see you are capping the lower limit and upper limit of the probability between 0 to 1. So, this is the solution of that problem where this probability goes beyond 0 to 1. So, this can be shown very effectively by this next slide, where you can see comparing the linear prediction and logit model. So, in case of linear prediction, you can see there are two outcomes, y equal to 0 and y equal to 1, these are two levels. So, in case of linear prediction model, you can see there is some it will go beyond 0 to 1. However, when we are using logistic regression model by converting into logit and predicting that logit by simple linear regression, ultimately you will see that logistic regression model will cap the probability between 1 to 0. So, that is why ultimately it is maintaining the assumption of linear regression. So, interpreting the coefficient, obviously the log of p by 1 minus p, alpha plus beta plus x here plus eta is error. So, the slope coefficient beta is interpreted as the rate of change in the logs or as x changes, which is not very useful, since p equal to exponential p basically assume this form. So, that is why an interpretation of the logic coefficient which is usually more intuitive is the odds ratio. So, since p takes the form p by 1 minus p is equal to exponential of alpha plus beta x. So, exponential beta effect is the effect of the independent variable on the odds ratio. So, here you can see outputs. So, households with pets at, you can see here 1.993 is ultimately the expected. So, the outputs with pets are 1.993 times more likely to evacuate than those without pets. So, this is ordinary logistic regression. Now, multilobial logistic regression is basically the is the same as logistic, it is an extension of logistic regression. So, basically it is used to model nominal outcome variable in which the log odds of the outcomes are modeled as a linear combination of the predictor variables. In our case, these are covariates. So, because we are dealing with categorical variables, it is necessary that logistic regression takes the natural logarithm of the odds, that is log odds, to create a continuous criterion we have already seen. And the logit of success is then fit to the predictor using the regression analysis. So, this is an example of multinomial logistic regression. As you can see, this is a most probable terrain class. Obviously, it is an area in Australia, and they have they have classified the total area. This area is called the Hunter Valley area, and so they have created these terrains, HVT01T, HVT011. So, most probable terrain class they have classified based on this multiple logistic regression, and this is an example how multinomial logistic regression is used for predicting terrains in digital soil mapping. Another is C5 decision tree. The C5 decision trees is another type of categorical model, and in this category it is basically based on the C5 algorithms of Quinlan, and this also you can see terrain class map created using C5 decision trees model. And again random forest can be used for both regression and classification, and here it is an example of classification. So, in this example you can see the terrain maps created using the random forest model. So, guys, we have completed this random forest the categorical models and creation of categorical models using using DSM technique. Again, to wrap up, categorical models are those where we are trying to predict some the categorical prediction models are those where we are trying to classify some categorical variables. In case of digital soil mapping, the categorical variables will be terrains. Terrains are basically some classification which has some connotation with related landscape models and soil farming factors, and this terrain can be classified based on several soil covariates. As we know, in case of continuous model, we use some covariates to predict certain soil property, and here also we can use those covariates or auxiliary variables to predict certain classes, and these classes are these classes can be predicted by using several types of categorical models, and these categorical models could be multinomial logistic model or C5 decision tree model or random forest model. And again, this multinomial logistic model basically assume that you convert the predictor variables into logits or log of odd ratios, which will help to which will basically help to give you to resolve the problem of finite outcomes in the target variables, and ultimately give it a linear regression forms, and ultimately using this multinomial logistic regression you can predict several classes. So, guys, I hope that you have learned something new in this last couple of lectures of categorical models and continuous model. In case of continuous model, we have discussed several important continuous model. We started with multiple linear regression, then we discussed about then the classification regression tree, which is a nonlinear model, and then we talked about QBist, random forest, and now we have discussed these categorical models, and all these are extensively used. Not only these, there are some other advanced models also which you do not have time to discuss right now, for example artificial neural network, and then ant colony optimization. So, all these advanced models which nowadays scientists are using for predicting certain soil properties through DSM, and these are basically we use for the Scorpion plus E formula. If you remember this function or soil spatial inference model, in case of that spatial inference model, we are using this mathematical models to predict certain soil property at a particular space. So, guys, let us wrap up here, and in our last lecture we will be discussing about Pareto transfer functions as well as some certain uncertainty measurements in associated with digital soil mapping. And thank you very much. Let us meet in our next and final lecture of soil science and technology. Thank you.